Carbon dioxide sequestration with spirulina algae. The reason I chose this project is I'm very interested in environmental issues and environmental preservation. I wanted to see if there was a natural method of reducing carbon dioxide that was less harmful to the environment. I immediately thought of algae, specifically spirulina, as it's a cyanobacteria, which means it's less harmful to the environment as it's actually edible by other animals. But specifically looking at spirulina, I wanted to see how effective it was at carbon dioxide sequestration, and I wanted to compare that with trees' effectiveness, which is the other leading natural method of carbon dioxide reduction. It was hypothesized that a lower population density, a pH level of 9, an outdoor environment with natural light, and fresh water would be the best conditions for carbon dioxide sequestration. To test this, first a culture had to be grown, using salts, nutrients, distilled water, and a live culture. It was grown over a period of 2 weeks, and it required very specific light and temperature specifications. A change to the testing procedure was made by adding in a hot plate and a water bath to go around the culture during growth. But once it was grown, then it had to be tested for carbon dioxide loss. Using the picture on the far left was my testing setup. A carbon dioxide canister was used to regulate the carbon dioxide level in the testing environment. A conditioned algae amount was added, and then I used a LabQuest and a carbon dioxide meter to actually measure the carbon dioxide change during testing. These tools allowed me to take data points every 15 seconds, which gave me a lot of data to work with. I conducted 12 tests and 4 control tests. This page shows the control tests. There was 3 different control tests conducted to show the carbon dioxide loss from all different methods during testing. One shows the carbon dioxide loss from water absorption, from leakage from the container, and then from the solution that the algae was grown in. The solution, actually a chemical reaction occurred between the sodium hydroxide that regulated the pH and the carbon dioxide in the testing environment. This was an unexpected result, and I put the chemical equation into the text on the right. While this result was unexpected, it still shows a very promising result at reducing carbon dioxide. This page shows the population density tests. The graph shows the carbon dioxide loss as time goes by. The black box in the middle shows the range from where the slopes were found, as well as the R-squared values were found. This way, there was an even comparison between the 30,000 and 40,000 ppm range between all of the graphs. To test the population density, 300 milliliters, 200 milliliters, and 100 milliliters of algae were tested, and it was found that 300 milliliters was the most effective. Using this information and the control data, a pie chart was made which shows the carbon dioxide loss from all different methods during testing. 7% was lost due to leakage from the actual testing environment, 2% was lost to water absorption, 42% was lost to the algae itself, and then 49% was lost to the solution, which was that chemical reaction that occurred. Now, even though the solution was more effective than the algae itself, the algae needs a solution to grow and survive, and therefore their carbon dioxide reduction goes hand in hand. This page shows the light, pH, and saltwater tests. The pH test had the most drastic differences in carbon dioxide reduction. The pink line shows the highly acidic test, which was the least effective at reducing carbon dioxide. This is likely due to the fact that during the conditioning process, the algae discolored a yellowy brown color, which meant the algae had died and therefore was ineffective at carbon dioxide reduction. The purple line shows the highly alkaline tests, and this is due to the fact that a chemical reaction was occurring between the sodium hydroxide used to regulate pH and the carbon dioxide. The light tests, the outdoor light and the indoor light, were about the same effectiveness, but both were more effective than darkness tests as photosynthesis couldn't occur. The saltwater tests, I found that any concentration of saltwater actually killed the algae, and I added in the control test with just a solution to show this trend and that all the carbon dioxide lost was actually just the chemical reaction occurring and not the effect of the saltwater on the algae. My most interesting result was the comparison between algae and trees. I found the amount of carbon dioxide reduction from the algae using my base algae tests. I found that it reduces 54.6 kilograms per meter squared per year of carbon dioxide, where trees only reduce 0.19 kilograms per meter squared per year. Algae is 300 times more efficient, which is a huge result. Now, there's a slight discrepancy in this result, as algae was tested in an environment of about 30,000 ppm of carbon dioxide, where trees are in ambient air, which is about 300 ppm. So this could have effect on why algae was so much more efficient, but still shows a very promising result. The main discussion point is the chemical reaction that occurred between the sodium hydroxide and the carbon dioxide during testing. This was a very unexpected result, but showed a very effective reduction of carbon dioxide. A repeatability was also found between 0.1 and 0.4 ppm per second of carbon dioxide reduction as I repeated the dark and the control test with water twice, where I found this rate. All my tests were done between 30,000 and 40,000 ppm, which was that black box on my graphs, and from there I found an R-squared value for all of my tests, which were above 0.96, which shows statistical significance. The image in the middle shows the conditioning of my acidic algae, which was the pink line on that graph, which was the least effective, and the discoloration is shown in the image so you can see why it didn't work, as the algae was actually dead. And the image on the far right shows how I found algae mass during testing. I was able to conclude that a high population density, outdoor light, high pH increased spirulina's effectiveness at carbon dioxide sequestration, and that salt, darkness, and high acidity will kill the algae and therefore make it less effective. But the most important thing I found was that an adaptation of the environment actually had an effect on spirulina's effectiveness at reducing carbon dioxide. These have amazing global applications at the moment, especially with carbon dioxide gas emissions and global warming, and algae is a really great future innovation to slow that carbon dioxide increase in the atmosphere. And these results, especially its comparison to trees, show promising possibilities for further research. This slide shows my 6 most important references. And this is my summary. Thank you.